And we're live! Welcome to RockSim Live. I'm Tim Van Milligan. I'm hosting today. I host it every day, every time, except for when Michelle was here a few years ago. So this is RockSim Live. This is where we talk about RockSim Pro, RockSim, and the Launch Visualizer, or mostly just general questions about rocketry. So I have the chat going. So if you are here, go ahead and say hello if you want to be recognized. And also put in your questions, because that's what we're here to talk about today, are your questions. We have Sturk03 from Pennsylvania. Liam Martin U2Y, and he has the first question. He says, can you show us the Mega Mako? Okay, and he is from Colorado Springs, so he's kind of like somewhere within like a 10-mile radius of me. And Johan de Sloper, and he says, built a Dutch to the max past 2 weeks, heaviest legal engine, and to 450 meter max, no permits, just Rocket Club member. Well, cool. Johan is in the Netherlands, so that's cool. Liam Martin says, yeah, I'm already a VIR. And Brian is here. Is Cecil Whiskey? Hello, this is Brian from South Bend, Indiana. Well, that's cool. I was in RockSim today. I was in RockSim Pro, and I was just looking for rocket clubs to launch from in the Launch Visualizer. And I was in Elkhart, Indiana, which is kind of like just southeast of South Bend. So, because I was saying, well, where is this at? And I panned out a little bit, and it was just near South Bend, so that was cool. Sturko3 says, Tim, could you go over your rocket you advertise as 2-stager that has electronically activated the upper stage? What's all involved to make that happen besides the cost of the rocket? Alfred Indy says, if I lived in Colorado Springs, Tim, you would be sick of seeing me hanging out at his shop. I'll tell you a little secret. I hide. But we do get a lot of customers that walk in and they want to say hello. And so I pop out every now and then like a little, what's that, little like a jack-in-box, just to say hello. A cuckoo clock. That's what me. I jump out of my little hole and then go back in. All right, so we got some questions, so let's get to it. Let me open up another window here to get the preliminary stuff going on. Let me share my screen too. Okay, so if you have never been here before, if you go to apogeerockets.com, this is our website, and if you sign up for our newsletter, you get 50 free rocket plans, but the plans are just kind of like a little extra bonus. The real meat and potatoes are the newsletters. Every week, it's kind of like every week we do something. So this past week, we put out a newsletter, and next week we're putting out a video, a how-to video. In fact, I was in my studio. I'm recording a whole series of videos right now. It's a mess. Behind me is a mess that you can't see, but here's rocket parts. That I'm working on videos, just more how-to videos, trying to give you the confidence to build creative and wild and crazy things. That's what we do here. We're here for you. But if you come here to our website, and if you click on this banner bar, we're at this time of year, we're on episode 218 right now. We're near the Christmas season, so we have some Christmas stuff going on right now. So we have a free Christmas tree topper. This is a link to the launch visualizer, which is at RockSim.com. We're having kind of some issues with RockSim.com right now. For some reason, our server got reset and it didn't reboot properly, and we need to try to fix that. But our programmer is kind of on hiatus right now. So yeah, so it's going to take a little while to get that going. But here is the RockSim 11 banner. And if you click on that, it'll take you to where you can buy it. But if you scroll down, here's a free 30-day demo you can try out yourself. There's other links here, how to use RockSim, system requirements, all the basic stuff. And if you go back up here to our menu, go to How To and Guides, click on that, and then come down here to Software. Basically, it's the same stuff. You know, the free trial, FAQs, system requirements, version history, and then you got tutorials here on this side. So we have RockSim tutorials, and then we have RockSim Pro tutorials. And if you're interested in RockSim Pro, if you go back to the home page, this one right here is you can get RockSim Pro virtually free, which means you're not paying for the software, but you're going to be paying for supplies. So you're going to be buying rocket motors and building supplies anyway. So you might as well get a free 30-day trial, and that trial can be extended month after month. So you can have it for virtually free. And then this kind of tells you how to get it. And I think we'll probably use RockSim Pro today in our session because it's just so fun to use. All right, so let's get to the first question. And that was Liam Martin. And he wanted to see the Mega Mako. So if you're on our website, just type in Mega Mako, and it will pre-populate, and we have the Mega Mako right here. You click on that, and this will give you all the information you wanted to know. I usually start here in these images, and if you click on these images, it will bring up a bigger version so you can see it. So this is what it looks like when it's assembled. That's what it looks like when it's launching. That's how big it is. It's a 4-inch diameter kit. Let's see, if you click over here, we can tell you it's 63 inches long. This is what it looks like on the pad. That's a rendering of how cool it would be to watch it. This is the shot cord mount, how it's mounted in the rocket. It's got a bridle inside so that we try to get it to hang as vertically as we can. It just protects the fins better. They're 1/4-inch fins, so they're not likely to break, but you know, any extra protection that we can do, we added it in that kit. You can get a motor retainer for it. This is a 54 millimeter diameter motor mount. It has rail buttons on it. It's because you're going to launch it off a launch rail. It has really cool decals, and they're printed on silver vinyl. So it's kind of like a mirror finish. Yeah, you can see them there. This is what you're going to get. You're going to get, you know, shot cord and parachutes and all that good stuff. And let's see if we scroll down on the page. Let's see if there's a video. Oh, here's a launch. So I'll let you click on the video to see it launch. This is Martin McKee. He is the designer of the Mako. It's a beautiful kit, and we're so happy to have it here. If you had a specific question about the Mega Mako, let us know in the comments here, and I'll try to get to them. Okay, so I had another question. Okay, Starko3 from Pennsylvania says, could you go over your two-stager that is electronically activate the upper stage? What's all involved to make that happen besides the cost of the rocket? Okay, so We got several rockets that are staging rockets, but the one we start with is the TTV. TTV stands for Timer Test Vehicle. So the timer controls when the staging happens. It doesn't have to be a timer, but we designed it around a timer. So this is what the kit looks like. It's called a TTV. It's a two-stage rocket. We got a booster, and there's a parachute right here. So to ignite the upper stage, we can't use direct staging where the bottom motor fires an ejection charge to the top stage. Can't do that with a parachute in the way. You're just going to fry your parachute. So in order to ignite that upper stage, we need to use electronics. And so there's electronics housed in this area right here of the rocket. And that's how big it is. That's it on the pad. That's it taken off. And also, you can't direct stage composite motors because composite motors have to be ignited from the top, not the bottom. So you got to get the igniter all the way in through the rocket motor, all the way up to the top, and you ignite it there, and that's what makes it go. That's the upper stage coming down. That's the kit. Okay, so here's kind of looking into the eBay, and we cut a porthole right here so you could see the blinking lights of the timer to tell that it was on. And it flies on a 1/4-inch launch rod. All right, so this is the partially assembled upper stage. So this is the motor mount, and then this is the eBay, and this right here is the simple timer, which we designed it around. But like I said, you can use other devices to control it, particularly the Perfect Flight Blue Raven and the Blue Jay Plus. Both of those will work as well as this. Again, this is the back side of the motor mount of the upper stage. The unique thing about this is it does have an ejection charge in that motor, and we got the electronics on the opposite side of this. This is the sled board right here. So in order to get the ejection charge past it, we had to build in a baffle system to vent that ejection charge so you don't blow your rocket apart. This is the electronics, and yeah, that's the whole kit. So his question is, what all do you need to launch this thing? So if we scroll down on the page, and we do this for all of our rockets, we don't want to hide what you're going to need. So on this particular rocket, I have a whole set of videos that guide you through the construction and then the actual launch of the rocket. So, so video number 13, let me scroll this up a little bit so you can see it. Video number 13 here says installing the ejection charge and the final prep for launch. So here is mounting the staging timer and the switch onto the eBay. So I'm going to walk you through it, so you're not going to be left hanging. But if you just want to know what you're going to need, just keep scrolling down here. Here's all the motors that will work. And there's probably more than this. This is we have a limitation on the number of combinations that we can do when we're doing staging. But there's a bunch to get you started, and then there's always the RockSim file that you can do more. And then these are, if you want to just fly the upper stage alone, you can use those. Okay, so down here is what you're going to need. So here's the basic tools: pencil, ruler, cellophane tape, masking tape, hobby knife, adhesives, blah, blah, blah. And then to launch, you're going to need a staging system to ignite the upper stage motor. So that's the important part right there. And then we have recovery wadding, rocket motors, igniters, igniters for deployment charges. So if you click on the staging system and igniters, those are the two. So I'm going to do this one in a new tab. Okay, so this one is the simple timer. And basically the way this operates is it's a timer. So it has to start, and then when it gets to the stop, it's kind of like a countdown. That's when it's going to ignite the upper stage. And it's got an accelerometer on board that detects liftoff. So as soon as the booster stage ignites and it starts going up the rod, it detects that and it says, okay, it's time to start my timer for the upper stage to ignite. And then so at a certain amount of time, I usually set them for like 2 to 3 seconds because the booster motor burns pretty short, 1 to 2 seconds. So if you set it 2 to 3 seconds, it's going to coast just a little bit, and then the upper stage is going to ignite. So typically that's what I set it at. Now, if for example, something bad happens, like the upper stage, it sends the current to the igniter to fire off the igniter, and you know what happens. Sometimes you push the button on your controller and nothing happens. Well, at this point, the rocket's going up and it's going to come back down, and we don't want it to come down ballistically. So the timer has built in a circuit that detects apogee. So as soon as it hits apogee, it's going to fire off the ejection charge for the parachute no matter what. If everything works fine, it's still going to fire it off. If it doesn't work fine, it's going to fire it off. So that when the rocket hits apogee, a parachute will come out, and so it will come down, descend slowly. So you have the option of using the simple timer for staging. And again, if you click here to related items, here is some of the stuff you're going to need to mount it. So you're going to need some kind of electronic device. So it's either a simple timer or one of the featherweight altimeters, the Blue Raven or the Blue Jay. Those will both work. So all three of them will work. But you're going to need a battery. And it doesn't have to be a big battery. I think the 400 milliamp hour LiPo battery is small and lightweight. If you have a big rocket and you have the room, the big battery, it's kind of like a gas tank. And you're sitting in your car idling. So you can idle for a long time with a big gas tank. Here with a smaller gas tank with a 400 milliamp hour battery, you can idle for only a little bit of time, or less. It's still a long time. Even our smallest batteries will give you, some of them, an hour. So you can sit on the launch pad waiting for your turn to launch, and then you're going to launch. You're also going to need altimeter mounting posts to attach the altimeter to the sled. You're going to need a tap in the drill set. And that's basically, you're going to tap into the wood and make threads into the wood. And that's what that does. And then you're going to need igniters for the motors and for the ejection charge. Remember that ejection charge at Apogee? You're going to need an igniter for that. So basically, that's the basic equipment that you're going to need. And yeah, let's see, if I go back here, so here's a staging system and then the igniters. So now, page not found. What is that? That was, I clicked on here, igniters for, oh, I see what it says. It says Quest Q2G2. Well, of course that doesn't work. I need to fix that. But now there is one trick you need to know for staging composite motors. And I got a video on that. And if you come down here to how-to and guides, come down here to advanced construction videos. Remember I told you that when you subscribe to our newsletter, you get videos? Well, these are the videos. And right now, I got 449 videos that are already on our website, and number 450 is coming on Tuesday. But on this page right here, we need to find the video. One of these videos out of 449 is about staging composite motors. So to find it, what you do is you do a Command F on the Macintosh or Control F on Windows, and that gives you a Finder window. And that just pops up right there. And I want to do staging composite. Okay, right here. How to stage an Aerotech motor. And that's what we want to do because they're composite motors. And this will show you how to stage those motors. Because they're a little bit trickier, and it all comes down to the igniter that you use. And the igniter you use depends on the motor. This is where it gets a little bit complicated. For small motors, like in the TTV uses 18 millimeter motors. So you're going to use an igniter for 18 millimeter motors. And the only ones that work on the Aerotech motors are the Aerotech igniters. And those will work with all three of those electronics that I talked about. The Simple Timer, the Featherweight Blue Jay, and the Blue Raven. Those, basically, you don't have to do anything to those. But when you're doing bigger composite motors, that's when you need to watch this. So if you want to do, now that you know how to stage using the TTV, then you're going to want to do something bigger and more exciting. And if you look behind me, it says the Invicta. The Invicta is our big two-stage rocket. If you type that in there and you click here, it comes up the Invicta. All right. But this is about RockSim, and I'm already 20 minutes in. So here we go. Let me go back. Oh man, you've been chatting while I've been talking. Liam Martin says, I'm 5 minutes away from you. Okay, well, shoot, you could be here and running this thing in 5 minutes. Gino145 says, hello from Boise. Brian says, Levi from Edwardsburg, Michigan. Sturko3 says, Tim, could you go over your... Okay, I just talked about that one. Alfred Indy retracted a message. Levi says he wants to say hi to you, Tim. He's a 5-year-old Rocketeer. Well, hello, Levi. Thanks for showing up. Liam Martin says, I mean, can you show us in person on the camera? Okay. Let me see. I am going to open up my chat, my internal chat. And I am going to chat to the front desk, and I'll ask someone to bring in the Mega Mego. Can someone, I'd say, please, please bring me the Mega Mego to the video studio. And if somebody shows up, we'll bring it out. Okay. Johan says, yeah, that TTV is cool. Francis Morin 1230 says it's a 4-inch and it's a big rocket. Yeah, it is. Johan says, as I build a fast model, I was also thinking about fin flutter. So I ran out of topics. So something you can talk about. Okay, I can talk about that one. Okay, so fin flutter. So basically, fin flutter, I got a rocket here in RockSim Pro. Oh, somebody's coming in with my big rocket. Somebody has to see it. Thank you, Martin. Okay, so here it is. Oh, you can't see it because I'm not showing the whole screen. Let me turn that on over here. This is a big rocket, so it might be hard to see. Okay, so we can just barely see it. Okay, so here is the Mega Mako. Now you can't see my face. Yeah, so it's got a 4-inch diameter nose cone. Right here is the eBay. I have to hold this up because I can't put it on my table because my computer's on the table. See the shock cord in there. Here is the eBay. Oh, look at this. It came apart. And let me see if there's... Oh, there's good stuff inside of here. Oh. That was the retainer. It fell off the table. Can you see it there? I got to get this right. There we go. So shock cord. Yeah, so here is a small, I think this is an 18-inch drogue chute. It's got heat shield in the bottom. Kevlar in here. Get this out of the way. Yeah, so here's the eBay. I wonder if there's any good stuff in here. Take this off. Unscrewing the little nut right there. Okay, so here is the eBay. There is some good stuff. We have a 900 milliamp hour battery over back here. Over here we have some terminal blocks. These are called terminal blocks. And basically this one was set up for 2 altimeters. We have one that was sitting right here. Right here are these 2 posts. And then the other one would sit up here. So it was kind of had dual redundancy into it. And then so these wires right here went to the altimeters, or maybe to the battery. No, to the altimeter. And yeah, and then there would be ejection charges that go out to both sides. There's little holes right here for the ejection charges. Yeah. So that would go into there. This side goes into there. And then there's a wing nut and a washer here on the back. So Liam, you're in Colorado Springs. You could come by and see it anytime you want. All right. Oh, and then in the top, there's a big parachute, and it just fell on the floor. If I try to bend over, I'll fall off my chair here. Okay, fin flutter. So here we have a rocket, and I don't like this rocket. So let me open up a different rocket. So let me open up Apogee. Avion. Save my changes? No. Okay, so that's the Aspire. Doesn't matter. This is actually a good one because this one could go fast. So this is the Aspire. And it's a minimum diameter 29 millimeter rocket. And let me load in a rocket motor. So choose an engine. Let's start with an Estes E15. That's kind of a sluggish rocket motor, but it'll work. And we'll click OK. So basically, I just loaded it back here into the rocket. And I did. Oh, you're not seeing my screen. Okay, so here is the Aspire. And I just loaded the motor here in the back. Yeah. And so RockSim Pro has fin flutter analysis. So did I mention that you can get RockSim Pro virtually free? So to use the fin flutter analysis, you go here to we want to go Rocket Design Components. We need to find our fins. So here's the fin set here. So we're going to double click on that, and it's going to open this up. And right here is the fin flutter calculator. And when you do this, it says maximum altitude, and that's not totally correct. We want to know the altitude the rocket is at when it's going the fastest. So this is kind of like right at engine burnout, which could be, well, for this rocket, engine burnout, it could be 3,000 feet up. Typically, they're a lot lower than that. And we'll find that out here in just a second. But to use it, we need to know the shear modulus. And the shear modulus is an engineering term. And if you want to really know what it means, we can go to like Google and ask, what is shear modulus of elasticity? And it says shear modulus is also known as modulus of rigidity, and it's a measure of a material's stiffness in response to shear stress. So shear stress is kind of like you're pushing on it in two directions opposite each other. Or if one end is fixed, you're pushing the end, kind of like a beam. Or in a rocket, you're pushing on it this way. So what we don't want is the rocket flapping around. And that's what fin flutter is, where the fin starts vibrating and actually flexing. And we don't want it to flex. And so in order to figure that out, we need to know that shear modulus. And then you can say, what is the shear modulus for let's type in stuff right, for balsa wood. And it's searching, and okay, and it says the shear modulus varies from 0.16 kilopascals for end grain balsa to well over 0.35 gigapascals. So we're going to take that number right there, somewhere in there. I'll use the low value here because that means that it's going to be more flexible. So the shear modulus, I want to make sure I got the right units. So I need megapascals. So I'm going to go, oops, I don't want that one, this one. Gigapascals. Okay, we'll use gigapascals. Okay, so we're going to use 0.16. So 0.16. And then as soon as I typed that in, it calculated the fin flutter speed. So if I change that to 0.32, you can see that the fin flutter speed is different, and it's faster. So that means the rocket has to get to that speed first before there's a chance that the fins are going to start to flutter. So a lower value is going to have a lower speed. So that's a more flexible material. Let's say, what's the shear modulus for soft rubber? So this is something that is very flexible, 0.003. So if I type in 0.003, so if these fins were made out of rubber, when my rocket gets to 35 feet per second or 24 miles per hour, those fins are going to go like this. Blah, 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 blah. Like I said, but you want to know what the altitude is, because this is going to determine, the density of the air that you're flying through. So first, let's figure out where our altitude of engine burnout is. So I'm going to click OK for here. And I've already loaded the motor in here. Did I make rubber fins? I think I left them at rubber fins. Anyway, let's launch. So I'm going to go prepare for launch. We have the F-15-6. I'm going to do, it doesn't matter about the streamer. We're just going to deploy to maximum ejection delay. Starting state, We're launching a 9-degree angle and at an azimuth, and this is like a compass. So north is here at the top, east is out to the side, south is here, west is over here. So we're kind of launching to the southwest. And leave that alone. Launch conditions. This is the Elkhart Rocketry Group launch site. See, I wasn't telling you a lie. I was looking at it. Let's do a flight profile. So this just kind of get the lay of the land, even though we don't need to know the lay of the land. And this is going to bring up the launch visualizer from Elkhart, Indiana. And I am on a grassy field in a, I think this is like a horse arena or a horse track. I think this is kind of like a county fair site or something. So where did I put my launch? My launch rod is right there, my launch pad. And if we launch this thing, it's going to be in the air for 88 seconds. We can already tell that. And we launch it. You can see the rocket's taking off. It's arcing into the wind. It's going high right now. You can see our altitude is at 2,800 feet. And at this point, the streamer has come out, and now it's descending down to the ground. And I'm going to speed things up and see where it lands. Right there, right along the road. So that's actually a pretty good landing. And this down here is called the mini view, and this shows up a close-up of the rocket sitting right here. So if we zoom in, you know, basically we get the same view. So basically we got two views going on, and we can see the trajectory and look around. And yeah, so that's our launch. If we want to get a rough estimate of where the rocket burned out, we can do that here. And what we're looking for is smoke, because when there's smoke, there's fire. Okay, so I'm zooming in. And the rocket is right here at the end of the line. Our smoke ends right there, so we need to back it up a little bit. Okay, so we can also see flame coming out here, so we do have fire. And if I put my cursor on the time bar and then I use the arrow keys on my keyboard, I can step through the launch. So at this point, at 3.41 seconds, we've reached burnout. And then if I look up here, we're approximately 1,383 feet. So that's an approximation. If you want more detailed information, we can get it here. We have altitude at deployment, maximum altitude, maximum velocity. And this is the speed that we want. Velocity of deployment, velocity of launch guide departure. I'm not seeing it. So if I'm not seeing the column, I can right click on this row right here, the upper row. I can click organize columns. And what I'm looking for is altitude at engine burnout. Let's see if we have it here. I'm not seeing it, so I can't get it there, but there's one more place we can look. If we double click on this last simulation, it'll bring up a detailed flight report. And this gives us a lot more information. So here's the launch guide data, maximum 8 data, maximum velocity, maximum range, maximum altitude, velocity at deployment, altitude at deployment. I'm not seeing anything. Maximum range. So we're going to go with the 1,380 feet. It's close enough. Yeah, it's not there. There's another place you can get it, and that's here in the graphs. So we can go time, and we can go altitude above ground level, and we can go, we want to know the maximum, we want to know the altitude of maximum velocity. So let's find velocity. Actually, we can go velocity here. We want relative velocity. This is relative to the ground. Absolute velocity is relative to the Earth's center, which is a difference because the ground is it like 4,000 miles away from the center of the Earth? So it's moving because the Earth is rotating. So if we go velocity and altitude, and let's end the graph at, when the rocket reaches peak velocity. Look at that, plot graph. Okay, so here is our peak velocity, and here is the altitude. So I'm dragging this, because I want to know the altitude of this point right there. So I'm going to drag it all the way over to here, and this is 1,000, 2,000, 3,000, 4,000, oh wait a minute, 1,100, 200, 300, 400. Okay, so it's like really close to that 1,380 feet. That's another way of getting the information. So now I want to go back here to our rocket design components, go to the fin set, and type in the value here, 1,380 approximately. Oh, and I lost my number, 0.16. And this was gigapascals, 0.16. So at that altitude, our flutter speed is 252 feet per second, or 172 miles per hour. So 172, remember that number. So I'm going to click OK here. And then I want to go back here to my flight simulations, to my last one, and I want to get my maximum velocity here. And my maximum velocity is higher than that 172 miles per hour. So I do have to worry about fin flutter here with this rocket motor and fin combination. So we got to do something about strengthening the fins. So that brings me to the newsletter. If you are not a subscriber, subscribe now, because our video on next week is how to paper fins to make them stronger. So now we have a composite material here. We've got paper laminated to wood to make them stiffer. And now your question is, how do I put that in the RockSim? And the answer to that is I don't know. Because now we need to know the combination, shear modulus, of this combination of paper on balsa wood. But you can use other materials as well. You can use carbon fiber or fiberglass. So if I say, what is the shear modulus for, I like using carbon fiber because the carbon fiber is like really good for fin skins. Shear modulus for carbon fiber. And we have 10 to 80. So let's say it's on the small end. Let's say it's 10 gigapascals. And so we go here to our fin set. And we say, what did we say this was? 1380. Oh, I didn't need a whole kit. Thank you. Somebody else brought in the whole kit. I'm talking to my friends. What do we say? It was 10 gigapascals. Oh, it's got to be gigapascals here. You got to watch your units. 10. So now, if our fin was made out of carbon fiber, our flutter speed would be 1997. So this is in like Mach, like almost Mach 2. It's really fast. Actually, it depends on the thickness too. So I have 0.09 inches. So if I was putting carbon fiber on a fin, I would ignore the balsa wood because carbon fiber is so much stronger than balsa wood that it's like the balsa wood's not even there. But now you have to consider what is the thickness of that carbon fiber, because, you know, thick versus thin, that makes a difference. So I would say my thickness here is, well, it's probably, I don't know how I'd estimate it. But you could say it's 0.01 inches. So even 0.01 inches, like that's not going to work. 0.09. Yeah, 0.09 works. I know it's going to be closer to that because carbon fiber we got a sandwich construction. So we'd have to do a little engineering. Maybe that's a good article. I have to remember that one. I'm always looking for articles for the newsletter. And if you're ever interested in writing an article for me, I would love to have it. If you're ever interested in writing an article, maybe this strikes maybe somebody out there is really smart and can figure it out faster than I can. What you do is you go to How To and Guides right here, come down here to PicoFlight Newsletter, and then come over here to Article Submission Guidelines. And this tells you how to submit an article, and you get paid for it. We pay $350 for a 3,000 word article, and it's prorated. So if you don't hit 3,000 words, you're going to get less. But if you try to fluff up your article, we're going to know about it, and we're going to condense it down to what is the meat and potatoes. Because we don't want to waste our readers' time. When you write an article, or when you subscribe to the newsletter, you want good stuff, and that's what we try to give you. Okay, so I think I talked about fin flutter to death. So let's see if somebody else has asked a question. We have Francis Moran. He says, just received some BT55 tubes today and an altimeter. Well, that's cool. I hope they were from us. And Mob Rocket says, hey, Tim, your What is DATCOM article in the latest PicoFlight was fascinating. I am not a rocket scientist, so I had to look up a few terms. A layman's term recap of this would be appreciated. So what is he talking about? He's talking about, oops, it's kind of like refreshed into something that's too big for your screen. If you come up here to How To and Guides, come down here to PicoFlight Newsletter, come to our last newsletter. That's not there. It should be number 666. How come it's not showing up? So 666 did not show up. How did that happen? But if you change the name there, and why did it open it up in Chrome extension? I hate that when it does that, or in the Acrobat extension. So anyway, if you do that, look at this. There's an AI that says summarize. Go away. Hide the bar. So this is the newsletter. This is the latest one that came out on Tuesday. And we talked about, this is what we talked about last week on the RockSim Live. We talked about how to use CD override. So I wrote an article about it, and it walks you through the steps. And see, like one of the things that RockSim does is it will pre-calculate the coefficient of drag, and it pre-calculates based on a system called DATCOM. And DATCOM was developed by the Air Force in it started in the 1960s, but they continually update it. And it gives engineers a very quick and dirty way of making CD estimates. And the second article in this issue is about what is DATCOM. So DATCOM stands for Data Compendium. Let's see if I can make this bigger. There we go. Data Compendium. It started in the mid-1960s, and they've got different versions of it. And the missile DATCOM is the one that we use. And this is open source from the government, because they want engineers to design good missiles. So they made it available. And this article gives you just a very simple synopsis of how it works. DATCOM's drag calculations uses component buildup, where each part of the rocket contributes to the drag separately. So the nose cone contributes drag, the body tube, the transition, the fins, the base drag, and any protuberances, like anything on the outside of the rocket, like rail guides and rail buttons. Those would be protuberances, and they contribute drag too. And in RockSim, if I cancel out of that, save my changes, no. If you go up here to Rocket and you do CD analysis, you'll see, and if I give it some velocity, so right now I'm at let's give it 127 miles per hour. At 127, the nose and the body tube contribute 57% of the drag, and it's estimated at 0.37. The base drag is estimated at 0.04. So the total drag is, when you add up all of these numbers together, you get this number right here. And that's how the predicted drag works. And that's how DATCOM works. It does it at the component level. And then the rest of this just says, why are we still using DATCOM today when there's new tools like CFD, computational fluid dynamics. So computational fluid dynamics is kind of like this, where you have particles in lines that move over the surface of the rocket, and then they start interacting and start causing turbulence. And computational fluid dynamics tries to calculate the coefficient of drag based not on the individual components, but on the entire system as a unit. And so it's pretty accurate. But why are we still using DATCOM? And the reason is because it's fast. Computational fluid dynamics to run a good simulation takes hours. So imagine you're designing a rocket and you change a fin. So every time you make a change to the rocket, the entire system has changed. So you have to rerun the whole thing all over again. Where in the DATCOM method, we're just changing a fin, so we just change the coefficient of drag of that fin, and then re-add up everything all together, and it's real quick. So the advantage of DATCOM is it's quick, and the results it gets you in the ballpark. It's close. It's not going to be exact. And that was the whole purpose of this article, is how to use CD override. So we're going to override the DATCOM method and plug in CD values for our rocket that we have measured. And how have we measured that? And we have articles, and this one explains in Picaflight newsletter number 651, we go through the process of using an altimeter data to measure drag. So we talked about the featherweight Blue Raven, which is a great altimeter for measuring drag. And so if I click on 651, it's going to open that. And it talks about how to measure the drag using altimeters. And the smallest one you can use is the Blue Jay Plus. It weighs about 5 grams. So it can be used for small rockets. For bigger rockets, I would use the Blue Jay, or not the Blue Jay, the Blue Raven. And then you also want, if you have extra room, then you also want to use a GPS electronics so you can get better positioning data. And so you basically, you get data, and then you come back here to RockSim Pro, and you can say, hey, RockSim Pro, I got this altimeter data. I've got a design right here. Help me figure that out. And then you go to this button right here. And this says, this button right here lets you compare CD, CP values from an uploaded CSV file. So that's from an altimeter data file. So your altimeter is storing data. You download that onto your computer, and then use RockSim Pro to open that data. And you can select your altimeter data file here. I don't have any on my computer, so otherwise I can show you. And then it will show you the CD. If you click this Advanced Results button, it will show you that CD data. And once you get that CD data, then you come over here to the CD Override tab, and you start populating this table right here. Basically, you're just going to populate the first two values, Mach number and A. That's all you need, really. And that's what the article tells you how to do it. We've got 4 minutes left. What do we got? We got Chuck Barnes from Pittsburgh. Hello, Chuck. Terry Wheelock from Texas is here, and he says, it's Rocket Day. Johan says, lovely topic. I literally heard it happen to model airplanes in a dive. Yeah, when you're on a passenger airplane, if you look out the window, we're talking about fin flutter again. If you see that wing going up and down, that's fin flutter. And airplanes are designed to allow for flutter, so don't worry about it. I don't think it's been a long time since a airplane, I mean decades, since an airplane had a broken wing because of flutter. I can't even remember. You know, recently we had a UPS airplane that crashed in, I think it was Tennessee or Kentucky, and it had a pylon that fell off. And basically what happened there was, over time, the engine was fluttering just a little bit, enough to cause fatigue. Fatigue is kind of like the metal got tired, and after it got tired, it started to crack, and eventually it cracked off. But wings are a lot bigger than the pylons that hold the engines on. And they are designed to flutter a little bit. I mean, some airplanes, like the B-52 bomber, the wings, they can stretch. I mean, they can go like 30 feet up and down, which is just incredible. They're flapping their wings like a bird. So you can see it, but don't worry about it. Tiny House Homestead says there is no empty space throughout the infinite universe. Space is a fluid, not a fabric. Ooh, now we're getting technical here. All right, so we talked about a lot today. I'm just looking for any other questions in here. I'm looking over here on my second monitor. That's what's going on. Just seeing if there's any other questions that I missed. Yeah, I think I got them all. You've been great. You've been asking great questions. You're making. I appreciate our team here keeping an eye on the chat. I was able to ask a question, and they were able to help, and I appreciate them so much. And I appreciate you for watching, and making us do this live, and for your questions every week. And I'm hoping that you're learning. I'm hoping that you're subscribing to our newsletter. And I hope you come back next week. We will be back next week. I'm not going anywhere. I'm here through the end of the year. What day is Christmas on this year? I better check that, right? Make sure that we're going to, where's my calendar? Christmas. Oh, Christmas is on a Thursday. Okay, so yeah, we'll be here the day after Christmas. Yeah. And that will be the last one of the year because that's the 26th, and then the January 1st is the next Thursday. And then we're going to be into the new year. Already 2026 is almost, it's hard to believe this year's it's gone by. The last few months have been a blur. Beginning part of the year, it seemed to drag a little bit because I was anticipating going to Serbia this summer. And, just that anticipation of a vacation, in Europe. And we went to Switzerland and all that. And so it seemed to go slow in anticipation. But then as soon as we got back, then things started going fast again. All right. Well, thank you for being here. I'll give you a countdown and we'll get out of here. So in 5, 4, 3, 2, 1, go out and launch something.